Welcome back. So I was mentioning about the notion of frequency. Okay, let us actually look at the DTFT of certain signals and then try to understand. Let's first take the discrete time sinusoid cos omega naught n. It's periodic. There are some conditions on omega naught for this to be periodic. We will assume that these conditions are satisfied. So this can be written as e power j omega 0 n plus e power minus j omega 0 n upon 2. Okay, which means that this has a frequency of omega naught and a frequency of minus omega naught. That's roughly what this means, right? Okay, but how do we now interpret this as a DTFT? So if you recall, in the previous video, we mentioned the existence of the DTFT only for absolutely summable sequences. And we also mentioned that the DTFT can be defined for other sequences as well. So let's take this. The constituent function is this e power j omega naught n. So let us actually define the DTFT for e power j omega naught n. Okay. So how do we get this? To do this, we should actually first look at the inverse DTFT. Okay. So the inverse DTFT, first, if you define what the DTFT is, the DTFT of a signal is x of e power j omega is summation, I'll say n is equal to rather, so it turns out that I mentioned to you about the Fourier series coefficients, right? So if you actually did the Fourier series based proof, you will find that you can easily just, basically the formula comes for free. The inverse DTFT is 1 by 2 pi integral minus pi to pi x of e power j omega n d omega. Notice the similarity to the inverse continuous time Fourier transform formula, and notice the similarity to the Fourier series coefficient equation. It's 1 by period over a single period of e power. There's just a sign change. Okay. In fact, you should go and do it. You will find that the relationship actually is that the Fourier series coefficients are x of minus n. So this is the inverse. Fine. Let us look at this e power j omega 0 n now. So what will give me, let's look at the reverse. What x of e power j omega should I plug in so that I can get xn is equal to e power j omega naught n. Now inside, notice that we have an e power j omega n sitting here. All we need is for this to evaluate to omega naught and come out. That's all, because the rest inside will just go away if you do that. So it turns out that we can define the DTFT of the sequence to be delta of omega minus omega naught. But hold, there is a slight mistake over here, because we said that the DTFT is actually periodic with period 2 pi. Okay. In fact, if you plug this in here, it will work, but this will work for any limits. For example, you can even do something like minus 20 pi to minus 18 pi. Sorry. Or you can do something like 103.2 pi to 105.2 pi. Also it will work. But this, if you plug in here, will not. So what do? In fact, this is not the exact way to write the DTFT. We are going to define it as summation k runs from minus infinity to infinity. Okay, there's a 2 pi also we want to get rid of. So I'm going to write it as 2 pi delta of omega minus omega naught plus 2 pi k. Okay, picture what does this look like? Okay, so let's draw a nice picture. Okay, so there is an impulse at omega naught, that's what this means, and at every multiple of 2 pi, omega naught plus 2 pi, omega naught minus 2 pi, and so on. Right? So you have at multiples of 2 pi you have many impulses. Now if you plug this into this formula, you will get this e power j omega naught n as the output. Why? Because if you take any period, let's say this is between minus pi and pi, notice that between minus pi and pi, this will just be this part, this will just be delta of omega minus omega naught. And what happens when you plug in delta of omega minus omega naught over here? You will in fact end up with e power j omega 0 n. Which means that for periodic signals like cos omega naught n, the DTFT is going to be minus omega naught, and let's say this is minus pi to pi. I am already assuming that omega naught is a number between minus pi and pi. We'll have an impulse here, I have an impulse here with weight half each. So notice that we are able to define the DTFT for sequences which are not absolutely summable. Of course, there is a catch. These DTFTs involve the use of impulses, and that leads to slight issues which you can think about in later courses. But for now, this is the way to define DTFTs. Okay, great. What about something else? What about UN? UN is another one of those sequences which does not have it's not absolutely summable. For UN, the DTFT takes a very special form, and that form basically uses the fact that UN is actually like this. UN is actually 0, 0, 0, and for n is equal to 0, and at n is equal to 0 it is 1, and then it's 1, and then it's 1, and then it's 1, and then it goes on. If you directly try to use formulas, you will end up making a mistake. Why? Let's have a look. Okay, let's start with the DTFT of something simple. Let's say delta n. Okay, we plug it into the formula. Okay, summation n runs from minus infinity to infinity, delta n e power minus j omega n. Notice that for every value of n this is 0 except n is equal to 0, so you get 1. Great. What about the shifting? Delta of n minus n naught. What do you get? You get summation n runs from minus infinity to infinity. By the way, n naught is an integer. Positive, negative doesn't matter. Delta of n minus n naught, e power minus j omega n naught. Sorry, e power minus j omega n. This is non-zero only when n is equal to n naught, and the result will be e power minus j omega n naught. Why? Because delta of n minus n naught is 0 for all values of n except n is equal to n naught. Okay. Okay, great. So let's now use this to find the DTFT of UN. What do we get the DTFT of UN to be? It's what UN will use the ingredients. UN is actually summation n runs from k runs from 0 to n delta of n minus k. Okay, so let me just check. Yes, so this so what is the DTFT of UN? UN is how do we express un in terms of deltas? So un is actually expressed as delta n plus delta n minus 1 plus delta n minus 2 and so on, which means the DTFT is going to be 1 plus e power minus j omega plus e power minus j 2 omega and so on. Okay. Now you can see that this looks like a geometric progression, and it is very tempting to write this as 1 by 1 plus e power 1 by 1 minus rather e power minus j omega. But there is a problem here. What is the problem? This summation is valid only when mod of e power minus j omega is less than 1, which it isn't. Okay, this summation of an geometric progression can be done only in the case where absolute value of the geometric progression ratio is less than 1. That unfortunately isn't the case, so you can't do this. Okay, so what do you do? In fact, this is an exercise which I will cover in a later lecture. Find out what the DTFT is, find out why it is that. Okay, the hint I will give you is that you can sort of think about it in terms of some symmetries and bringing symmetries into the picture, but find out what the DTFT of UN is and find out why it is defined that way. I will cover it in a subsequent video. Okay, thank you.